Good morning, and thank you for coming. And first, I'd like to thank the organizers for giving me the opportunity to give a talk here. I will talk about the discrete convex functions, and so the title shows extension ramifications. So there, actually, there's no mic. This is on. But you can't hear me, or it's better? Oh, okay, I will try right there. Okay. So first, we should start with Lovasz' very famous paper in 1982. And it is from, so you see here, this is a math programming symposium in Bonn here. And in his paper, the title, Submodular Function of Convexity, he says 3 important features of convex functions. Okay? And they are here. So the convex function occurs in many contexts. There are many models. So that gives us motivation and application of convex functions. And convex functions admit a lot of operations or transformations. Okay? Maybe you can think of any. And they give them the sufficient structure for theory, which is mathematically beautiful and practically useful. That's a difficult thing, actually. Usually, it's easy to find a theory which is useless, but convex analysis is one of the best theory. And also, algorithm works. So these are features of convex functions. And his point is that this is also the case with submodular functions. Okay? And I'd like to use this slide to change into discrete convex function too. So the issues that we are interested in discrete convex analysis is these 4, maybe. Okay? But with some question marks. I do not claim that these are already done in discrete convex analysis, but we are interested in these too, these 4 features. In this talk, I will fill in this table. Okay? Here, a number of different discrete convex functions, concepts, and here are some characteristics. And so some history. So matroid was introduced in 1935 by Whitney, but recently it was recognized, but some Japanese made a comparable contribution. And Edmonds was the first to discuss submodular functions in the context of optimization. And then this is 1969, is the year of Professor Erie's book. Maybe you're not very familiar with it, but this is my supervisor and the father of a Japanese school. And here he talked a lot about the convex functions within the context of network flow, and with emphasis on electrical circuit. So this gives us the physical meaning of convex analysis. Okay? And 82, that is the year of most important year for submodularity and convexity. So the Lovasz explained a lot about it, especially Lovasz extension of convex submodular function. And Anjan Frank here formulated discrete separation theorem, which I will explain later. And Fujishige also formulated in the Edmonds intersection type theorem into Fenchel-type minimax duality. Okay? All these 3 are rather independent, but they are really a kind of insightful observations. And then people realized that, okay, submodular function is a convex function. That's it. And nothing significant happened several years. But in 1990, independently of these observations, variated matrix was introduced by Legendre-Fenchel from algebraic point of view. It has nothing to do with optimization. And by Fubati and Tardella here, the concept of integrated convex function is defined as a kind of extension of this Lovasz extension. And this year, or a bit later, I started to advocate discrete convex analysis while I was in Bonn. Yeah, so the Bonn is an important place for me. And then so this year, or maybe 1 year later, for paper, the combinatorial algorithm for submodular function minimization appeared. And that made the whole area very practical. Okay? And these are the new generation that I'm going to talk about today. So M-convex function on jump system and L-convex function on graphs. Okay? Now, classes of discrete convex functions. So I deal with these 7 classes. The first generation is fundamental. Submodular set function, separable convex function, almost obvious, but integrally convex function that I'm going to define. And L and M convex function, or with some symbol, L natural and M natural equivalent notions. They form the main classes in discrete convex analysis. And these are extensions. Now the definition, you know submodular functions, fine. You know separable convex function. Separable convex function means that fx as convex function that is represented as the sum of univariate convex functions. So x is a vector, and each component appears here, and each function looks like this. This is non-convex, this is convex. If there is only one variable, then it's easy to define what convexity is. Okay? Now, the integrally convex function. So this is a concept which formulates the consistency between convex extensibility and integer lattice. Okay? These two are sort of different concepts are merged. So for given real vector like this, the integer neighbor is defined like this. So if x is in the middle of the unit cube, this is 4. And if it is on the boundary, these two are neighbors. And local convex extension of a function f is given on the integer vertices, and we want to define convex extension. So in each unit cube, we can consider, there's a form of consider our convex extension. So remember that every function on unit cube can be extended to convex function. It is independent of Lovasz extension. Okay? So this is defined, and we glue them together. So in each hypercube, we have convex function, but it doesn't mean that collection of them defines a globally convex function. But if that is the case, then the given function is called integrally convex. Okay? Now, for the set version, it's easier. So if you have such a 4-element set, then take the convex hull. Then this is somehow convex. But the definition of this integrally convex function says that take each convex hull, take convex hull in each square. So we have 4 of those, and we take the union that gives the original convex hull. That's why this is integrally convex. But in this case, if we consider local convex hull, then this is fine. But here, we have only line segment. The union doesn't form convex set. So this is not integrally convex. This is a concept. Is clear? Okay. Now, so local convex means that in each unit hypercube, we can define convex extension, independent of submodularity. Okay? So here, look at this. We have only 2 points in this square. So the convex hull of these 2 points is just a line segment. So this is local convex hull. But if we make the union of this, then the resulting set is not convex. So that is why this set is not integrally convex. Fine. So the function classes actually look like this, although I didn't define this concept yet. So f is defined on integer points, and subclass is convex extensible function. Convex extensibility means that there exists a convex function in real variables which coincide with your function at the integer point. And subclass is an integrally convex function. And separate convex function here. And the main classes in discrete convex analysis is M and L convex functions. They look like this. And submodular set function that you are familiar with is a subclass of L natural convex function. Okay? So actually, L natural convex function defined on 0, 1 vectors are exactly the same as submodular set function. Okay? And here are extensions. The first here, so from here, they are suitable for modeling bipartite graph or network flow. But of course, you are interested in non-bipartite matching. Good morning, Andras. You can still catch up. And so actually, jump system is his favorite object. And so matching theory and non-bipartite graph. So this doesn't fit in this framework, so the concept is generalized. And recent progress is to extend this concept to functions on graphs. This was done by Hirai to deal with the multi-flow problem. Okay. And here is varied CSP. If you have any questions, please ask Stand, not to me. Okay, so these are backgrounds. So here is a list of motivation applications connections to other fields. So submodular functions, so you have many applications in your mind. So. But here I just mentioned that to deal with connectivity problem in graphs, we do need crossing submodular. Okay? But crossing submodular, this type of variations is not really captured in discrete convex analysis. Okay? Or rigidity. Also, yesterday we heard about this. So not really the submodular function, but it has some small variations. So these should be considered later. And separate convex function, there are many applications. In particular, resource allocation problems, they talk about a lot on separate convex function. And integral convex function, what is the motivation? I asked him, and then we agreed that this is not really motivated from real problem, but it's a mathematical aesthetics. I mean, there's consistency between convex analysis and integer lattice. Okay? And L and M convex functions are primarily motivated by network flow problem, single commodity network flow problem. But it turned out that L convex function is now used in image processing because energy function there is a typical L convex function. Or operation research, but in particular inventory or scheduling. And about inventory, Tom McCormick will give a talk. And for M-convexity network flow, or not here at tension, but here at flow. And recently, Fujishige and others wrote a paper with a congestion game where M-convexity plays a role. Or in economics, the concept of the substitution is equivalent to M-convexity somehow. So there is a lot of work. And so Akio Shiora will talk about it today in the afternoon. And actually, mixed polynomial matrix is just some linear algebraic problem. This was a real motivation for me. So I wanted to solve this problem, and that's why I invented this intersection problem. But this is a very minor problem, but I will never explain about this. And so then the new generation, the M-convex function jump system, was introduced to deal with the degree sequence on graph, non-bipartite graph, or matching problem, the constraint matching problem. And Yusuke Kobayashi will talk about this. Or there's another paper from Blendon, which connects this combinatorial concept to algebraic notion of half-plane property of multivariate polynomial. Or finally, the L-convex function on graph is introduced by Hirai to solve the problem in multi-flow or multi-facility locations. Now, here are some references you might read. And actually, this is Fujishige's famous book, Yellow Book, and this is this book. And if you're interested in my real motivation of matrices, then you may look at this book. And recently, another book appeared from the logistics context that they deal with L-convex functions extensively. Okay, so any questions so far? Any requests so far? Okay, so we have defined these three already, and we go on to the four. So L-convex function, L means lattice. And here the notation, P and Q are vectors, and this is the component-wise maximum and component-wise minimum. And function G on the integer lattice, integer vectors, is L-convex if it is submodular in the ordinary sense, and moreover, it is linear in a special direction. So there exists some constant independent of position P, such that if you increase the component by 1 uniformly, then the function value increases by R. So in this direction, this function behaves linearly. And in applications, it oftentimes, this number is 0. So if R is 0, then all the function values are the same in this direction. We have one extra dimension. So instead of considering function on Zn, we may just drop one coordinate to define the function on this coordinate plane. This is L natural convex function. Okay? And, or in other words, a function G in n variables, L natural convex, if we define a function in n plus 1 variable with extra variable P naught, and that function defined by this, P minus the uniform decrease or increase. And if this function is submodular, then the original function is L natural convex. So this might be easier to understand. And it turns out that, so by definition, L-convex function in n plus 1 variables is isomorphic to n natural convex function in n variables, but it turned out that it contains a class of L-convex functions. Okay? And here's a simple remark. So what happens if there's only one variable? Is this function submodular? It is. This is submodular function. So if we consider this picture, this is two-dimensional picture. If we have only one dimension, so one of these are equal to the one of those. So as a union, so this function is submodular function, has nothing to do with convexity. So any function, every function is submodular. But we do want to discuss the convexity, so we usually consider this type of inequality, which is equivalent to L natural convexity. Okay? Is this clear? Now, here are some examples. So L natural convex functions, maybe there are many, but the submodular set function is a particular case, and energy function of this type, or I don't know the proper name of this function. It's a tension. It's in network flow problem. It represents a tension, cost of the tension. Okay, this is L natural convex. Okay. Now, another class, M-convex function. M stands for matroid. And this is a generalization of matroid exchange property, or polymatroid exchange property. So EI denotes ith unit vector. And if you take 2 points, x and y, and pick any coordinate I with xi strictly greater than yi, like this, x is to the right of y, then there exists another index j with inequality reversed, such that if we exchange I and j between x and y, then the function value decreases or remains the same. This is a definition. Okay? So intuitively, if we have 2 points x and y, and in a sense, x and y comes closer while respecting the integer grid, then the function value should not increase. Okay, this is compatible with the intuitive concept of convexity. So for convex function, if we come closer a little bit, then the function value decreases. And here, actually, it turns out that the domain of definition, that means where the subset where the function value is finite, is on the constant sum hyperplane. Okay? Because of this. So this is correspond to the axiom basis in matroid. The bases have equal cardinality. So similarly, the domain of definition must lie in a constant sum hyperplane. So then instead of considering this hyperplane, we can project to decrease one dimension. Okay? And this is called M-natural convex function. And the exchange axiom for M-convex function, of course, is inherited by this projection, and it turns out this. This is the exchange axiom for independent sets. Okay? Not only exchange of I and j, but we may be able to increase and decrease. Okay? And similarly to L-convex functions, we have such an inclusion here. So these are the definitions. And here's an example. Say, for this type of cardinality convex function. Okay, so given any convex function, and inside is a cardinality of set function. This is M-convex function. Okay? Or for quadratic function, we have such a simple criteria. Actually, this is pretty much related to discrete metric, okay? Trimetric or ultrametric. Okay. So, any question about L and M convex functions? Okay. Then some extensions to jump system. So jump system is defined in terms of exchange axiom, but it looks like this. Or it may have some holes. Okay? And constant parity jump system satisfies this type of simultaneous exchange, which I learned from Jim Gillen 20 years ago. And when I saw this, then immediately I can consider the similar exchange axiom for functions defined on jump system. That's it here. So if we take x and y in the jump system, and we know that we can exchange if that is a constant parity jump system, then we impose this condition for x to be M-convex function jump system. And it has a motivation from the paper by Apollonio and Shebo about mean square factor problem. So this formalism generalizes their approach. And later, this concept, or this weighted case, has application in factor problems, so two matching or So one of them is called Yusuke Kobayashi's talk today. Okay. Now, very recent introduction of L-convex function graph. This is pretty much complicated, but I will spend 1 minute to tell you what it is. Okay, so here is an integer lattice on which L natural convex function is defined. And he introduced the concept of L-convex function on so-called oriented modular lattice, or modular graph. But this is difficult to define, so let us specialize to trees. It is already interesting. And actually, this case was already treated by Kormork and others. So here we have a direct product of two lines. That gives us two-dimensional integer lattice. So instead of chain, we consider tree and another tree here. Not necessarily isomorphic, two independent trees. And you consider the direct product. It looks like this. And we assume that orientations are given on edges. So in Kolmogorov's approach, it was a rooted tree, but here, any directions, so arbitrary directions. And also here we have direction. Now, it's strange. Let's return. I skipped one slide. Sorry, I returned to the L natural convex, but this was the most important slide. I wanted to use this slide, but now I realize. Okay, again. To be kind to you. So L natural convex function is defined in this way, but it admits a number of equivalent characterizations. And one of them is translation submodularity. Here, we have extra parameter alpha. So if alpha is 0, then this is just a submodular inequality. But it imposes this inequality for every non-negative integer alpha. So this is stronger than submodularity. And this is equivalent to L natural convexity. This is the first characterization. And second is midpoint convexity. So here, we have P and Q integer vectors, and we consider the middle point. And in the usual convex function, the function value here is smaller than or equal to the average of the two endpoints. But since we are working on the integer lattice, this point may not be integral, so we round up and round down consistently for all components. And this is a notation for rounding up integer point, and this is for rounding down. So this inequality first appeared in Favati-Tardar's paper. And in a joint work with Fujishige, we could show that this inequality is equivalent to L natural convexity. Yeah, so maybe it's the easiest to, maybe this inequality is easiest to understand, maybe. But this emphasizes submodularity, okay? And they are equivalent. Now, we jump into the graph again. So we have this, remember? And so here is, this is a generalization of integer lattice. So suppose we have 2 points, x and y, and I'm going to define midpoint convexity. Okay? So how can we define the midpoint? So in the formula, this looks the same. But the meaning of this notation should be made clear. So if x and y, so component-wise, x is here, and y is actually here. Yeah, if you look at the first component. Then the middle point, x and y, is somewhere here. So we round up or we round down. But since we assume that there is a direction of edges, so one is rounding up, the other is rounding down. So head or tail. And if you look at the second coordinate along this tree, the middle point x and y is somewhere here. And then if this is directed, then we can also define the rounding up and rounding down. So we end up with these 2 points. So this gives a condition for a function to be L natural convex, L convex on direct product of trees. So this was the definition. Okay, and so for the trees, the previous works on submodular function with the trees or k-submodular function. These are special cases. Now I have defined all these concepts. Yes. Yes.
Should it be obvious to me that there is some, I don't know, that this geodesic between x and y?
Oh, yes, yeah.
Somewhere, and then it's not so obvious what it means to go up and down.
Because we assume that there is some direction on edges. So we are now here in the middle. But because of this direction, we assume this is downwards. Okay, so we are here. But look at this direction, and then we go down here. This is rounding down. And if we look up above, then we go this way. So the rounding down and rounding up are defined with respect to the given orientation. Okay. In the integer lattice case, we have a chain and consistently ordered. So in this tree case, also you could say that there is a root and there's an arborescence, and then you can define similar construction. This was done by Kolmogorov. But here I show that this also gives us a concept, and it's useful. It's okay? So I have defined those classes. Okay? You don't have to remember. Yes?
So when I add up 2 L-convex functions, it's still L-convex.
Oh, yes. Yeah.
It's not true for all these.
Good point.
Maybe,
Yeah.
which of them are?
Maybe already at this point. I can answer. Or maybe, okay. It's true. So I answer your question. So if you consider the addition of 2 convex functions, submodularity preserves it, it's fine. Separable, fine. Integral convex, not. It's strange, but it's not true. And L convex, fine. But M, not true. It corresponds to matroid intersection. If we consider 2 matroid and intersect, then it's not matroid. And this, because of this, some of the M convex functions not M convex. And this is not either, because this is a generalization of this. And 3, this is true. So L convex function in different versions can be added.
Everything with L.
Yeah, L is fine. M is not. Okay, yeah. Good. So here's the classes. So almost the same as you saw before. But I added M convex and L convex function. But conceptually, M and M natural are equivalent if we increase variables by 1. But if we fix M here, we have such an inclusion. Okay? And those 2 or new generations doesn't fit this picture. Okay? Now, let's look at the special case of set functions defined on 0, 1 vectors. Then the picture looks quite different. Not contradictory, but quite different. Okay? The first, every set function is integrally convex. So integral convexity or convex extensibility doesn't make sense. And submodular set function is exactly the same as L natural convex function that I told you. Okay? And some of M natural concave function form a nice subclass of submodular function. This is somehow surprising. Concave function is submodular. So people here not everybody, is interested in maximizing submodular function under matroid constraint. And people know that this is a difficult problem. But if we restrict f to be a subclass of submodular function called M natural concave, then it fits in this area, and this can be solved exactly in polynomial time, in strongly polynomial time. Okay? So this is a evaluated matroid intersection algorithm that I found in 1996. Okay. Now, what operations can be done? We have already talked about addition. Okay? That here addition, sum. Okay? And convolution. But today, I would like to concentrate on transformation by graphs on network because of the time. So here's just a list. Okay? So for L, always yes, yes. Okay. M, no. But instead of this, if you consider convolution operation, which is actually dual to addition, then situation change the opposite. Convolution of M-convex functions, yes. This corresponds to matroid union. If you have two matroids, the union is again a matroid. But this is yes here. And for jump system, this is also true. And in Yusuke Kobayashi's talk, he will make use of this fact to derive some result. Okay? Now, what is transformation by graph network? So maybe you know that if you have a bipartite graph for simplicity, if you have some matroid structure, you can induce that structure from left to right. Okay? The subset on the right is independent if it can be matched to an independent set on the left. This is a well-known construction. Then the function version of this is a given the function f on vertices here, and maybe cost function, linear cost function on the edges. And if you have y here, you look for x, which matches y, such that f of x, the function value on the vertices and the function value on the edges, is minimum. So you can define a function g in this way. So it induces function f through the graph. And we know this is as a special case, convolution is a kind of this operation. If we have such a graph, this construction gives us a convolution operation. Now, we know that if the given function is M-convex function on the integer points, okay? So in that case, this is not matching, but network. And then the induced function is, again, M-convex. So we could prove it. And also, this generalized to jump system. Okay? But the proof is much more complicated. And now the big question. You. Okay, the question is that, so is this function, the construction general enough? So again, the given graph and the edge cost and the matroid, so now we don't have any function on the left side. This is just a matroid structure. And then the induced function is M natural convex, as a special case of my previous theorem. Then Andreas Frank asked me already 10 years ago, maybe 8 years ago, whether this construction exhausts all the possible M natural convex functions. Okay? So this problem, please solve it. So I also mentioned this problem again in the program session. This is so fundamental, but I couldn't really get it. Okay? So there are many young students, people. Yes?
What is the simplest function you know, which is not known whether it can be?
Actually, I don't have any. So if you have a matrix, polynomial matrix, that gives us another class of M natural convex function, which is independent of graph. So this class would be the possible counterexample. But still, my intuition is that this works. So that we are given those vertices, but we can choose a big, very big bipartite graph. So we can choose this. The function is given on the right-hand side, and we can choose S, C, and not F, but matrix structure here, the huge matrix, or on a huge ground set. So maybe, and this is not necessarily bipartite. So you can use a very complicated network. That's fine. Okay, so this is a question that I want to solve. Now, for the transformation by network, this is a status. Okay? So L and M actually transformed, but they are kind of conjugate transformations. So I will explain a bit later. But for matroid, we know that matroid is transformed to another matroid. That means the rank function is transformed to another rank function. But the formula is not that one. So there's another one. So that extends the L-convex function. Now, what properties are there? So in convex analysis, we talk about those properties. The first is the global minimum is characterized by local minimum. This is the first property that everybody have to consider. And then maybe algorithms or proximity theorem for scaling. On these are really structural properties, conjugacy, but the dual, the concept of dual can be defined or not. Or the separation theorem, duality holds or not. Or minimax duality. These two are related, almost equivalent, but they look different. So I go on to the first issue, the minimization. So for all the classes, we have a theorem of the form that given point is global minimum if and only if it is local minimum in an appropriate sense. The local minimum should be defined in which, with respect to which neighborhood. But all the convexity concepts satisfy this. Probably otherwise, people do not call this convex function. Okay. So for integrated convex function, the point x star is optimal if and only if it is optimal within this neighborhood, plus minus 0 vector. Actually, there are many such points, 3 to the nth, and there's no polynomial time algorithm. But it's not surprising. This is okay. Now, for M-convex function, the neighborhood is much smaller. We only have to consider this type of 1, minus 1, and 0 elsewhere. So we have n square such vectors. So the neighborhood is so small that we can check directly the local optimality. And for M-jump system, similarly, we have more combinations, plus or minus, but still n squared in order. So, where's L? Oh, it skips. For L, this is interesting. For L, here is a point. The neighborhood is 2 hypercubes, above and below. So P star plus minus 0 vector. So twice 2 to the nth. So the size of the neighborhood is exponential, but this can be checked in polynomial time using submodular function minimization. So L natural convex function, when restricted to 0, 1 vectors, it is a submodular set function that you can minimize. So here you minimize, and if it's this, okay. And if you minimize, if the minimum is attained by this, then you are guaranteed that this is global optimal. Okay? So the complexity for this is n fifth to the fifth, or yesterday I learned this is decreased to n to the cube. And anyway, this is called polynomial. Okay? So summarizing this, so we have this inequality for all the classes, and the sizable neighborhood are here, the polynomial, the integrally complex and L-convex are exponential. But for L-convex function, in spite of that, we can still polynomially decide whether they are locally optimal or not. And moreover, we can design algorithm for global optimization. Okay. Good. Now, some structure. Any questions? Maybe should we take rest? Okay, then the structural theorems. So what is conjugacy and duality? Well, I distinguish between these two words. In matrix context, conjugacy means the equivalence of exchange axiom and submodularity of rank function. So matrix can be defined either in terms of exchange axiom or in terms of submodular functions, and they are equivalent. So this is conjugacy. But duality means something like matrix intersection type theorem. So we have two matroid or two submodular functions. We have some special statement. That is duality here. Okay. Now, to formulate the conjugacy, there is a standard construction using Legendre transform in convex analysis. So given the function f here, you consider tangent line, and if you draw many tangent lines and you erase the original function, you can still see the original function. So that means that tangent line has the information enough to recover. Okay? If the given function is not convex, then this is just a disaster. Okay? And so in formula, this is conjugate function defined as the maximum of something. This is the inner product, linear function minus given function. So this is a usual construction, except that maximum is taken over integer vectors, because the function is defined on integer vectors. And if f is the integer valued, then the resulting function is just of the same type. Maybe I skip this. Or maybe I should. So given the polyhedron, the polymatroid, from polyhedron, we can define submodular function according to this formula. And no. Given the submodular function, we define the polyhedron according to this formula. And conversely, given the polyhedron, the submodular function is restored by this. And this phenomena can be formulated as a conjugacy between M and L-convex functions. For this polyhedron, we associate the function of indicator function by S, which takes 0 inside S and outside plus infinity outside S. And here we have a Lovasz extension. And these two are related by that formula. So now we have conjugacy theorems for L and M convex functions. So L and M convex functions are defined independently so far. But actually they have one-to-one correspondence. Okay? Just like the matroid defined in terms of family of subset and also in terms of rank functions. And as an immediate consequence, we have biconjugacy. So if you start from here and apply this transformation and apply again, we return to the original position. This is the biconjugacy. Sorry?
So in convex analysis, if you take any function,
yeah,
the transform is convex.
Okay, that's a good point. Okay, I will explain it. Okay, so in convex analysis, or maybe you had more question. Sorry. What was your question?
The question, if you start with a not an L-convex function, if you take the transform, does it become L-convex?
No. So if you start, so these are in one-to-one correspondence. So if you start from here, you cannot jump into here. If you, okay, so this is really restricted to this area. Okay, but I'm not saying that this is the best possible area, so we can expand a little bit. We know to preserve this. So here's the history of discrete conjugacy. When Edmund discussed polymetric and submodular functions, they have the one-to-one correspondence. There's a conjugacy. But later, around 80 or 90, there are independent generalizations to evaluate the matrix and submodular integrated convex functions. And these are separated into different directions, so they lost conjugacy. Then, using this larger framework, we restore the conjugacy for M and L convex functions. Now, what is the significance of a conjugacy? It is just nice, but it has physical meaning. In electrical network, X means current in a branch, and P is voltage, potential. Okay? And in economics, X means commodity bundle. It's a vector representing the quantity of goods. If I buy this amount, buy this amount. This is a vector of X. Then P is a price vector of the commodities, of goods. And if we have biconjugacy, we can develop a discrete DC program, difference of convex function programming. This is our recent work, and it derives discrete version of Tolan-Zinger duality. This is another kind of duality. Okay, now the duality, what was that? So first, here's a very simple property which I recently looked at. So this looks trivial, but not the case. So suppose F is convex in some sense, and minus F is convex. That means F concave. Is it linear? In the ordinary case, that is true. In real variables, a convex function which is at the same time concave function, that is linear. But submodular function, if that is a set function, that is true. If set function submodular and supermodular, that is modular, that is well known. But if you consider submodular function on the integer lattice, that is not the case. As you saw, for n equal 1, any function is submodular and supermodular. So that doesn't imply that is linear. So some complications. And separate convex function we have, yes. But for integrated convex function, no. Because any function on the unit cube is integrated convex. Okay? So we don't have such a natural statement. And L and M, we could prove. Actually, I worked out some months ago. It's not easy. And for M convex function, it's even worse. There's a counterexample. This is a former student of mine, a very simple counterexample showing that this is not true for M convex function on jump system. So it is called convex function, but it's not really convex. It's an annoying phenomenon. So the answer no implies there's no separation theorem. Okay? Not conversely, but if we have no already here, then we cannot hope for any discrete separation theorem. Well, what is discrete separation theorem? In the generic form, it said that if f is convex and h is concave, then there exists a hyperplane linear function in between. And if the function f and h are integer values, the separating hyperplane must be defined by integer data. This is a discrete separation theorem. And the most important result, I skip this, is Anders-Frank's discrete separation theorem for submodular supermodular set function. It is found in 1982. Okay? But maybe I should do it. But the difficulty of discrete separation that for such a simple example, we do not have integral separation, just in two variables. We cannot. This shows that in general, the separation theorem is not true. And also here, this is another example that even the real separation is impossible. So, but fortunately, for M-convex and L-convex functions, there are theorems known. And once, so this is a summary of the status. Okay, here the separation theorem, submodular function yes, separable convex function. This is easy, and integral convex not, but L and M yes, and jump not. And this is not really formulated yet. So I don't say no, but nobody knows how to describe it. And once we have a separation, and assuming some conjugacy stuff, then the minimax relation can be derived almost automatically. So we have the same answer for this. And the minimax theorem looks like this. So we are given f and g, M convex and M concave, and this is Legendre transform, the conjugate function for convex function that I explained. But for concave function, we have infimum here, okay? And Fenchel duality theorem. But here, infimum and supremum are taken over integers. So nonlinear integer function duality. Okay? And it implies this Edmond intersection theorem or Fujishige-Fenchel duality theorem, not a special case. So here's a summary of my talk. Well, well, how can we appreciate it? Okay, first, look. So separable convex function is fine in all respects. So all the answers are yes. Okay? So operations and minimizing a conjugate duality. And next, here. So local optimality characterizes global optimality. So all the answers are yes. Because so we understand this would be the prerequisite for this class to be called convex functions. Okay? Now, look at L and M convex functions. They're pretty good, but here's some N here. But these are actually, so maybe if you have good eyes, there are two kinds of N, blue N and black N. Okay, here the N here, here, and here. And blue N are so-called controlled, so we understand what it is. Okay? So submodular function, the convolution is not true, but it corresponds to matrix intersection. Okay? So that's fine. So in the same way, this no is fine, because we know that conjugate is yes. And here it's okay, because this conjugate is yes. And other black N's are sort of unfortunate. Okay. Okay, so thanks.
Any questions or comments?
So what about optimization? Can you find the global minimum?
Minimum? Okay. So you ask algorithms. Okay. So I showed the slide for minimization here. And at the end, we have this here. It shows, so this means the criterion. And here the local optimality can be checked or not. And this is a complexity for global optimizing algorithm. I didn't explain the details, but based on this or scaling technique, we can develop the weakly polynomial algorithm usually. Okay. Yes.
They said there's duality between L-convex and M-convex for the interior lattice. So for the generalizations, you know the kind of dual. So if I have an M-convex function jump system, is there any kind of duality?
Actually, that's an interesting question that I thought about it, but it's not really true. Yeah. Also, the Fujishige was one of the persons who really liked to know it, so he has some paper. Yeah.
Any others? Regarding the summary, there are also these natural classes, right? Is there something? So the table is too small.
Yes. Okay.
Is there something notable about the natural?
Okay. So the L and L natural is not distinguished here. So actually, you mean this? I should have another row for L natural. You mean?
So I'm asking if there's something maybe that behaves differently for these natural classes.
Oh yes, but it is almost equivalent. So, oh yeah, same. At least this part is exactly the same. Yeah. So if you consider the proximity theorem and the upper bound like this, maybe I skipped it. Here is a proximity theorem. So this is the minimum of the alpha scaled function, and this is the original real minimum. Then this n is turned into n minus 1 for L-convex function. Okay? But such a small change might be needed, but essentially the same. Okay.
Any others? Now and then